guys, welcome to chemistry class. Today we're going to be learning how to do ideal gas law calculations. Now, the first formula you need to know how to do is how to convert Celsius to Kelvin, because you cannot do ideal gas law calculations in Celsius degrees. Always has to be Kelvin. So the formula you're going to use is K, that's Kelvin, equals Celsius plus 273. And we're just going to leave that up there for future reference, because you're going to need it. So, our first problem. Divers gets the bends if they come up too fast, because gas in their blood expands, forming bubbles in their blood. If a diver has 0.05 liters of gas in their blood under a pressure of 250 atm, that's pressure units, then rises instantaneously to a depth where his blood has a pressure of 50 atm. What will the volume of gas of his blood be? So we're looking for volume. So what equation do we use to solve this ideal gas law problem? Well, we're dealing with volume here and pressure here. So what would that be? Boyle's law, exactly. Now what's Boyle's law? Boyle's law is P1, I'm just going to write it up here, P1 times V1 equals P2 times V2. Now for this equation, you could go ahead and solve for the variable that you're missing, but I find it easier sometimes to go ahead and just plug and chug. So I'm just going to write down my units and the stuff that has been given to me in the problem, and we're going to write it down in the equation. So 250 atm times 0.05 liters equals P2, right over here, 50 atm times X. That's V2. That's what we're looking for. So how do we solve this problem? We need to isolate X. So what do? Divide both sides by 50 atm. So 250 times 0.05 divided by 50 is, dun dun dun, 0.25 liters. There you go. Way to go, guys. Okay. See, and remember, you cross out to check your problem, you cross out your units, and you see that I'm left with liters here, which is the unit for volume. So I know I set up my problem correctly. That's just a little way to check yourself. Okay, on to the next one. The temperature inside my refrigerator is about 4 degrees Celsius. If I place a balloon in my fridge that initially has a temperature of 22 degrees Celsius and a volume of 0.5 liters, what will the volume of the balloon be when it is fully cooled by my refrigerator? So again, we're looking for volume. But I hope you notice we're not going to be using Boyle's law, because we're dealing with temperature and volume, not pressure and volume. So what deals with temperature and volume? Charles' law. And Charles' law is, we're going to write it down for reference, V1 divided by T1 equals V2 divided by T2. We'll just finish erasing that. Okay. Now we've written it down, but we can't start plugging in our numbers yet because we have to change Celsius to Kelvin using this formula here. So what are our values? 273 plus 4 equals, I'm just going to cross this out, and it's going to become 277 Kelvin. And this 22 plus 273, we're going to cross this out, and it becomes 295 Kelvin. So now, let's plug and chug. So V1, that's volume 1, 0.5 liters divided by T1, which is 277 Kelvin, equals V2. Remember, that's the variable we're looking for, so we're going to put a big X there. Divided by T2, which is 295. Now here, we're going to cross multiply. So it's 0.5 liters times 295. And what's that? 147.5. And 277 times X, 277K times X. And like the other problem, we need to isolate X. So it becomes, we divide both sides by 277. I forgot to write down our units, but up here we would have liters and Kelvin, and we would cross out our Kelvin. So we're left with liters, which again is a volume unit. So 147.5 divided by 277 is 0.53. Way to go, guys. Okay, on to the next one. Now, make sure you guys are following along at home. Try to work out these problems. Pause the video when you can to see if you can get ahead of me. And then just come back and check your work, because that's how the video will be most beneficial to you. So, determine the pressure change when a constant volume of gas at 101.3 kPa is heated from 25 degrees Celsius to 35 degrees Celsius. Now you're probably freaking out because we have never seen kPa before. But, don't, because we're looking at an entirely different formula. We're looking at Gay-Lussac's law. And Gay-Lussac's law states that P1 divided by T1 equals P2 divided by T2. And kilopascals is just another unit to say pressure, so don't freak out. Now, again, we're looking for, according to the problem, we're looking for the pressure change. So we have our P1, we have our T1, and we have our T2 in Celsius. We have to convert them to Kelvin, so I hope you're following here. 25 plus 273, 298 Kelvin. I'm just gonna forget about the Celsius. It's not important. We don't need it here. 35 plus 273 is 308. So there. That's our new formula. So now, let's plug and chug. P1, 101.3 kilopascals, divided by T1, 298 Kelvin, equals P2, our variable that we're looking for, big X there, divided by T2, 308 Kelvin. So now we cross multiply, which it comes out to 31,200.4 kilopascals and Kelvin equals 298 Kelvin times X. Also, again, isolating X. Are you kind of sensing the repetition here? It's really simple, really simple. Just the more you practice, the more you get it. Isolate X. Divide 298 Kelvin from both sides. Run out on the board, but that's okay because we're almost done with the problem. So 31,200.4 divided by 298 is, get your calculators out, ladies and gentlemen, 104.70 because you're going to round. So that's that problem. Man, we are just flying through these. All right. On to the next one. Whew. If I initially have a gas at a pressure of 12 atm, and a volume of 23 liters and a temperature of 200 Kelvin, and then I raise the pressure to 14 atm and increase the temperature to 300 Kelvin, what is the new volume? Don't freak out. I can see it in your eyes. You're thinking, this is so many variables. What are we going to do? See, we have a formula for that. This is called the combined gas law. And the combined gas law formula takes into account Charles, Boyle's, and Gay-Lussac's law. This is P1 times V1 divided by T1 equals P2 times V2 divided by T2. Now, thankfully, we already have our temperature in Kelvin, so we don't need to do that calculation that we've done before. Now, we're just going to look, cross-reference. What do we need? We need volume. Volume's in the top. So, we're going to plug and chug because that'll be a bit easier for us. So, 12 atm times 23 liters divided by 200 Kelvin equals 14 atm times x, our variable, divided by 300 Kelvin. And we're not going to cross multiply just yet. We're going to go ahead and multiply our top numbers, and then we'll see where we go from here. So 12 times 23 is 276 atm and liters divided by 200 equals 14 atm times x divided by 300 So now we will cross multiply. I'm going to write it over here so we have enough room. So it's 276 times 300 is 82,800 atm, liters, and Kelvin equals 200 times 14, which is 2,800 atm, Kelvin, and x. So there we go. We're going to isolate x again. So divide both sides. 2,800 atm, Kelvin, 2,800 atm, Kelvin. Cross out our units. Left with liters. Look at them. Liters is a volume. Cross out our units over here. I like crossing out my units. So 82,800 divided by 2,800 is, calculators, ladies and gentlemen, 29.6 liters. Woohoo! Very good. Excellent job, guys. We just got one more. Bear with me. Bear with me. I hope you guys are getting a sense of how you just gotta look at your problem, write down the units that you're given, write down all the variables, kind of assess what formula you're going to use, write it down, just be organized about what you're going to be doing. Okay, if 4 moles of gas at a pressure of 5.4 atm has a volume of 120 liters, what is the temperature? I've said it before, I'll say it again. Don't freak out, because again, we have an equation for this. This equation is the ideal gas law. The only time you're going to use the ideal gas law is if you have moles. So as soon as you see moles in a problem, you know that's exactly the one you're going to be dealing with. Okay, so let's write down our equation. PV equals nRT. What this R stands for is our constant. Now, you look at the units of your variables, and that determines what constant you're going to use. The constant we're going to use today is 0.0821 L times ATM divided by K times mole, because those are the units we have. So I'm just going to write that up there. Now let's go. So for this equation, it's a lot easier when you solve for what you're doing. So we're going to divide both sides by N and R. That becomes T equals P times V divided by N times R. Let's plug and chug, ladies and gentlemen. 5.4 ATM times 4 moles divided by N, which is our moles. Oh, see, I knew I would do something wrong eventually. That's wrong. It's our volume that goes up there, 120 liters. Sorry about that. 120 liters divided by 4 moles, and then our constant, which you might be thinking, don't freak out, trust me. We're just gonna flip the constant. When you divide by a constant, you're just gonna flip it, like this. Times 0.0821 liters, atmosphere, and then we're gonna put Kelvin and moles up top. Simple. Just flip it when you have to divide by the constant. So let's finish off the math. 5.4 times 120, 648 ATM times liters times Kelvin times moles divided by 3.284 moles, liters, and atmospheres. Cross out your variables, cross out your units so that you know you've done the math right. Moles. We're left with Kelvin, which is our temperature unit. And to do the math, it is 197.32. Let me know if you guys have any questions. That's been our ideal gas loss calculation. I hope you've learned a lot, and I'll see you guys in my next video.